It is my pleasure to announce our speaker, giving the third lecture in the 55th Annual DeLong Lecture Series. Professor Barry Simon is the Emeritus IBM Professor of Mathematics and Theoretical Physics at Caltech. He has made deep contributions in both mathematics and physics, including work in the fields of analysis, functional analysis, quantum field theory, statistical mechanics, Brownian motion, random matrix theory, non-relativistic quantum mechanics, random and ergodic Schrodinger operators, orthogonal polynomials, and spectral theory. He has over 400 publications, more than 20,000 citations on MathSciNet, and a Google Scholar H-index of 114. He is the co-author with Michael Reed of the foundational 4-volume series, Methods of Modern Mathematical Physics. His 5-volume text, A Comprehensive Course in Analysis, was recently published by the AMS. He has had over 120 co-authors and 30 graduate students. Simon received his BA summa cum laude in physics from Harvard University in 1966 and his PhD in physics from Princeton University in 1970. After graduating, he joined the faculty at Princeton as an assistant professor in mathematics and physics and became a full professor by 1976. Simon joined the faculty at Caltech as the Sherman Fairchild Distinguished Visiting Scholar in 1980. He joined the faculty permanently at Caltech in 1981 and became the IBM professor there in 1984. Simon spoke at the International Congress of Mathematicians in 1974 and has given numerous other prestigious lectures in mathematics and physics since then. He's a fellow of the American Physical Society, the American Academy of Arts and Sciences, the American Mathematical Society, and the U.S. National Academy of Sciences. He has served as vice president of the American Mathematical Society and of the International Association of Mathematical Physics. In 2012, he was given the Henri Poincaré Prize by the IMAP. The prize is awarded every 3 years in recognition of outstanding contributions in mathematical physics and accomplishments leading to novel developments in the field. In 2015, Simon was awarded the International János Bolyai Prize of Mathematics by the Hungarian Academy of Sciences. Simon was awarded the 2016 Leroy Steele Prize for Lifetime Achievement by the AMS for his tremendous impact on the education and research of a whole generation of mathematical scientists through his significant research achievements, highly influential books, and mentoring of graduate students and postdocs. In 2018, he was awarded the Danny Heinemann Prize for Mathematical Physics by the APS. Before I turn over the microphone, I will give a few words about the DeLong Lecture Series. This lecture series is funded by an endowment given by Professor Ira M. DeLong, who came to the University of Colorado, excuse me, in 1988 at the age of 33. Professor DeLong essentially became the mathematics department by teaching not only the college subjects, but also the preparatory mathematics courses. Professor DeLong was a prominent citizen of the community of Boulder, as well as president of the Mercantile Bank and Trust Company, organizer of the Colorado Education Association, and president of the charter convention that gave Boulder the city manager form of government in 1917. After his death in 1942, it was decided that the bequest he made to the mathematics department would accumulate interest until income became available to fund DeLong prizes for undergraduates and DeLong lectureships to bring outstanding mathematicians to campus each year. The first DeLong lectures were delivered in the 1962 to 63 academic year. With that, I will turn over the microphone to the speaker.
So having heard this, I now thought about something. Did he regard himself as a bank president who was moonlighting as a math professor, or a math professor who was moonlighting as a bank president?
It's a very good
question. Unusual combination.
I don't know if he gave money to the bank association as well.
Anyhow, today I'm talking about more tales of our forefathers. This is not a mathematics talk, but it is a talk for mathematicians. It's independent of the Tales of Our Forefathers talk that I gave last week, but you might not have heard of, but I've tried to avoid too much overlap. Oh, I'm not sharing the screen again. Is it sharing now? Not yet.
Not quite yet.
Let's try again.
We did test beforehand. It was just working.
Yeah, well, it's sort of worked now.
Yes.
I want to make the same introductory caveats I made last time. I'll be a little briefer. I'm not a historian. I have no faith that everything I'm saying is true. None of the stories was made up, at least by me. I regret this is mainly about forefathers, not foremothers, although there will be one female mathematician among the 22 that I discuss. A third caveat is that I'm an analyst, and I learned many of these stories when working on notes for a series of analysis texts that I've written. So I'll be focusing on analysts, but prior to the 20th century and mathematicians, prior to the 20th century and some extent in the 20th century, mathematicians were more universal, and so analyst means most mathematicians. Mostly we remember mathematicians by applying their names to theorems and mathematical objects. And in this regard, I want to remind you of the Arnold principle: if a notion bears a personal name, the name is not the name of the discoverer. So the bulk of the first talk was structured around families and life events like death. I decided to start this talk with an amusing parlor game, which is admittedly a little silly, especially if one takes it too seriously. I've organized the talk around groups of 3, leading to a total of 22 mathematicians. In the modern era, there's enough infrastructure that many great mathematicians quickly found important positions and lived rather dull lives. But lack of university positions, limited contact means this is less true of the greats of 150 to 250 years ago. So the game is, who are the 3 greatest mathematicians? I dare say for most, the top 3 listed alphabetically are Euler, Gauss, and Riemann. Although I should point out that when I gave this talk in England, someone came up to me afterwards and said, not at all. Everyone knows it's Euclid, Archimedes, and Newton. But I dare say most people would come up with these 3 names, but there are 6 groups of mathematicians when it comes to their orderings. My own personal ordering is Riemann, Euler, and Gauss. I won't make a big deal of this personal choice, which you can see. Many put Gauss first. As I'll explain, it depends on what you give Gauss credit for, which is a very complicated issue, as I'll explain. So George Georg Riemann began as a student in Göttingen, where Gauss was, but Gauss was not really concerned with students, as we'll see when we get to him. He actually spent his career as the head of the observatory in Göttingen, not as with a associated position in mathematics. So in 1847, when he was 21, Riemann moved to Berlin, where Jacobi, Eisenstein, Steiner, and especially Dirichlet influenced him. Interestingly enough, as unintended payback, Dirichlet got credit for work on harmonic functions, so that the terms Dirichlet problem, Dirichlet principles, Dirichlet boundary conditions are all named after Dirichlet, because Riemann learned of these things in Dirichlet's lectures and named them after him. In fact, Gauss, Green, and Thomson had preceded Dirichlet, whose work was actually only published in 1850. So it pays to have a good student. He can name things after you. Riemann, shown here quite young, and here actually not long before his death, returned to Göttingen in 1849, where he spent the rest of his career. Among his students was Dedekind. He always had a sickly constitution, and he died of complications of pleurisy at the age of only 39. 2 of his students, Hankel and Roth, also died at early ages. Hankel, I suspect some of you have heard of his functions, and this is the Rach of the Riemann-Rach theorem. Namely, they died at ages 34 and 26, respectively. What is most amazing of Riemann is he actually only has about a dozen papers, several of them posthumous. There are 6 multifaceted masterpieces, and I want to emphasize what is in individual papers. So he has one paper that began by defining the Riemann integral as a preliminary to the discussion of Fourier series. He then went on to prove his version of the Riemann-Lebesgue theorem, lemma, and what's called the Riemann local convergence theorem. Another single paper has all his basic complex analysis. So this is in one paper: Cauchy-Riemann equation, the Riemann removable singularities, the Riemann mapping theorem, and the notion of Riemann surfaces of functions, all in one paper. He has a single paper in which he developed all of Riemann geometry, starting with the notion of a metric, using that to define geodesics, and then using that to define Riemann curvature. There's the celebrated short, I think it's 8-page paper on the Riemann zeta function, which includes its functional equation, the Riemann hypothesis, and his vision of how to use the zeta function to understand the distribution of primes. There are papers on higher dimensional theta functions that includes his version of Riemann-Roch and the Riemann approach to hypergeometric functions and monodromy. So that's Riemann, but it's just amazing how much he squeezed into short papers. So I talked about Euler in the first talk, so I'm going to just summarize some of the main points. He was raised in Basel. His family expected him to be a pastor, but Johann Bernoulli convinced Euler's father to let him be a mathematician. He spent his career employed by academies of science, first in St. Petersburg, then in Berlin, and then returned to St. Petersburg again. A remarkable thing is he was totally blind from 1766. He died 17 years later, but continued to produce many papers until his death. He wrote with the help of scribes and mathematical assistants. He was remarkably prolific. Among other things, he had 13 children in both mathematics and physics, and has complete works running to 72 volumes, each in the 400 to 700 page range. To show his influence, I want to quote the results of a 1988 poll in Math Intelligentsia, where it asked readers to help it pick the top 10. I'll get to what it was the top 10 of in a second, which had Euler with 3 of the top 5 in this poll. I'd heard, when I first heard about this, I was told it was the top 5 formulae. That made sense, but it turns out it was actually asked about the top 10 theorems, which is crazy because in the list of top 10 theorems, it didn't include Cauchy integral theorem, the spectral theorem, or the prime number theorem. But again, Math Intelligentsia has a very mixed readership, many of whom are math junkies rather than true mathematicians. No matter, here are the top 5 on the list, which shows Euler's impact. And remarkably, all 5 are mathematicians whose names start with EU. So the 5th, we're going to do this a la whatever that late show was, Johnny Carson, I guess. Johnny Carson, anyhow, whoever it was. The number 5 formula is the Basel formula. There was a conjecture, there was a question of the Bernoulli brothers, what this sum was in closed form, and Euler was actually able to compute it as pi squared over 6. Second is the fact, the theorem of Euclid, that there are only 5 regular polyhedra. Third is the theorem of Euclid that there are infinitely many primes. There's Euler's polyhedron formula that for any polyhedron in 3 space, suitably defined, what you mean by a polyhedron, of course, the vertices plus the faces minus the edges is 2. And finally, there's the famous formula that e to the I pi plus 1 is 0. And here are some stamps that show Euler. Gauss was a young prodigy who came to the attention of the Duke of Brunswick. He actually came from a relatively poor background, and this Duke supported his attendance at what is now the Technical University of Braunschweig. Then he paid for him to go to Göttingen, and finally to Halmstadt, where he submitted his dissertation to Pfaff of Pfaffians. And the dissertation actually had his first proof of the fundamental theorem of algebra. In 1801, he published his masterpiece on number theory, and in that year gained great fame for the following. So there was an asteroid series that was discovered early in the year, but there were only a few observations before it went behind the sun. With then current techniques, the orbit could not be accurately predicted. So people wondered where it was going to appear. And Gauss used what we would now call the method of least squares and determined the orbit well enough to predict where it would be found. Indeed, it turned up there, and this caused a big stir. And on the basis of this fame, unfortunately, just about this time, or it was fortunate he did it then, the Duke, his patron, was killed in the Napoleonic Wars, but just in the nick of time, because of this work on Ceres, he was able to get an appointment at the observatory in Göttingen. Interestingly enough, two of Gauss' contemporaries who were good friends, namely Bessel and Mobius, also spent their careers as astronomers. Indeed, Bessel really was not a mathematician in any sense of the term. He actually had no real serious education, did numerical fits originally, but eventually he did did discuss Bessel functions for astronomical purposes. Gauss spent his career as the observatory director. In addition to his pure mathematics, developed techniques in magnetism, geodesy, and potential theory. Indeed, his work on both Gaussian curvature and Gauss's law had roots in this applied work. Gauss's mathematical contributions are staggering. Among the contemporaneously published ones are he turned number theory from a set of odd hoc observations into a systematic field. He discovered quadratic reciprocity and was stated what's now called the class number theorem. He found the first proof, found several proofs of the fundamental theorem of algebra, which, by the way, does not say in those days what we think of it as saying, namely that every complex polynomial has a root, when therefore factors into linear factors. It rather said that every real polynomial factored into linear and quadratic factors, because people didn't think about complex numbers in the same way back then. He invented Gaussian curvature, used the notion to state the first version of the Gauss-Bonnet theorem. There's Gauss's law, the formula for div, and his work on harmonic functions. He did fundamental work on hypergeometric functions. He invented a method of numerical integration called Gauss quadrature. He did least squares. Perhaps even more impressive than this list is the work that he never published. That's why you can argue what he should be getting credit for, because some of them were only published after his death in his complete works, and included in this. So in 1811, he wrote a letter to his friend Bessel that included a statement without proof of a version of the Cauchy integral theorem. Cauchy actually only found the integral theorem 14 years later, but Cauchy published it. Who gets credit for that? In 1832, he wrote to Janus Bolyai's father, who was his student. So this is the Janusz Bolyai is most known for, he's one of the co-inventors of non-Euclidean geometry, but his father was also a mathematician and was a student of Gauss. And he wrote to the father of Janos saying, oh yeah, I discovered non-Euclidean geometry many years ago. I don't understand. I thought I turned that off. He also discovered what's now called the first Fourier transform, actually even before Fourier's work. The first Fourier transform only appeared in his complete works, but was basically forgotten until it was rediscovered by Cooley and Tukey in 1965 in quite a dramatic situation. The algorithm came at exactly the right time, just as digital computers became powerful enough to compute Fourier transforms of data important in the real world, and there was an explosion of applications. In fact, Tukey came up with the basic algorithm in the following manner. He's basically a statistician, but he was a member of President Kennedy's Scientific Advisory Committee, and the committee was trying to figure out how to analyze seismic data to get information on Russian nuclear tests. And overnight, between the 2 days of the meeting, Tukey came up with this fast Fourier transform as a way of analyzing data to get the Fourier transform. Dick Galwin, who was from IBM, was also at the meeting, and he put Tukey in touch with Cooley, who actually coded the algorithm for him. Gauss also discovered the invariant measure for the Gauss map, the map that takes x into the fractional part of 1 over x. This is relevant to the theory of continued fraction expansions of reals. He never published it, but it was not rediscovered before it appeared in his complete works. It appeared in an 1812 letter to Laplace, which also stated without proof the connection to the asymptotics of continued fraction expansions. So without knowing about the ergodic theorem, from the invariant measure, he guessed what the asymptotics of continued fraction expansions would be. He conjectured the prime number theorem when he was 15, but published nothing on it. He mentioned in a letter 50 years later, oh yeah, I observed this when I was 15. In 1827, Abel and Jacobi revolutionized the theory of elliptic integrals by understanding that their inverse functions were doubly periodic, what we call elliptic functions. But in his notebook, starting about 1796, Gauss had this basic idea, at least for a special case called the Lemniscate integral. So it's an elliptic integral that describes the area, the arc length of a lemniscate. The question that's fascinated historians of science is why Gauss left so much unpublished. One factor is summarized in his statement, few but ripe. Another is a famous statement he made about Dirichlet. The total numbers of Dirichlet's publications is not large. Jewels are not weighed on a grocery scale. I think I'm going to skip this part because it's not nearly so interesting, but the slides will be available, and so you can look at this. There's a story about some probably incorrect history of science. Okay, so that's the first group, the top 3. We'll play one more round. What about the next 3 on the list? And here I claim people would come up with different groups, and no doubt Archimedes and Euclid would be at least on this area, but not for me. For me, the next 3 are Newton, Hilbert, and Poincaré. Newton is, of course, not only a great mathematician, but arguably the greatest physicist. His only real competition is Einstein, I know the physicist Landau thought Einstein was the greatest physicist, and it's hard to argue. They both are spectacular. It's not only for laws of mechanics and gravity, but also his work on optics. His greatest mathematical discovery, of course, was Fluxions, known as calculus, but he also found the binomial theorem for fractional powers, the notion of repeated divided differences, and did some basic algebraic geometry, was the first person to classify cubic. But to think about subjects misses his truly historic contribution to civilization. Before him, explanations of nature were all mainly magical. Afterwards, the world became a dynamical system. So the idea that nature is described by some set of differential equations, which really is behind virtually all of fundamental physics, is a Newtonian realization. As Alexander Pope put it so Pope is a famous British poet, nature and nature's laws lay hid in night. God said, let Newton be, and all was light. To which a later British poet added, it could not last. The devil shouted, ho, let Einstein be, restored the status quo. Here is Newton on a £1 note. I won't focus in detail on the tales of the young Newton, who made some of his greatest discoveries while home from Cambridge during a plague scare, nor on his priority fight with Leibniz, both of which are well known. Of course, one feels a certain kinship to Newton when we talk about plague scares. Instead, I note that while we think of him as the great rationalist, he spent almost as much time studying alchemy as physics. He wrote religious tracts. Indeed, he studied the Talmud. The Hebrew University has this remarkable set of notes that Newton wrote on the Talmud in Hebrew, or in Aramaic, in fact, I believe. He was a director of the Mint in his later years, and actually some economic historians say the only reason Britain became an economic powerhouse is because Newton rationalized the currency. That's Newton. Next, Hilbert. So Hilbert was a giant with contributions to algebra, geometry, analysis, and logic. His students include Bernstein, Blumenthal, Courant, Dane, Haar, Hecke, Hellinger, Kellogg, Knesse, Lasker, that's the famous chess master, has a PhD in mathematics, Schmidt, Steinhaus, Weil, and Zermelo. He was born and got his PhD in Königsberg, and in that university was where he met and became lifelong friends with Minkowski and Hurwitz. This is Hurwitz, the complex analysis. There's also a Hurwitz that I think is spelled slightly differently, who was a topologist. That's later. In 1895, at age 33, with the backing of Klein, he was appointed a professor in Göttingen, where he spent the rest of his career. There was not always pleasant competition with the University of Berlin and its faculty. His early work involved aspects of algebra, particularly invariant theory. There's something called Hilbert basis theory and algebraic number theory. His 1899 book, Foundations of Geometry, re-examined Euclidean geometry with, for example, axioms about what it meant for one point on a line to be between two others. In many ways, 1900 was a pivotal year for Hilbert. This is, first of all, the year when he presented his famous list of problems, but in the next year, he heard Erik Holmgren, who was a Swedish mathematician, talk about the work of Fredholm on integral equations. which was based on the development of a theory of infinite dimensional determinants. To me, in an act of real bravery, because Hilbert was by then 40. Everyone knows no mathematicians do anything good after age 40. He totally switched fields. He had not done analysis before then. He switched into analysis, and other than some work in logic, spent the bulk of the rest of his career studying analysis, especially integral equations. He was very successful, although not as successful as he hoped. According to Hellinger, at that time a student of Hilbert, when Hilbert announced his seminar would be devoted to the study of integral equations, he declared he expected to be able to use them to prove the Riemann hypothesis. By the way, he was not alone. Many years later, first Faddeev and then Lax and Phillips, or maybe it was, had the idea of trying to realize the zeta function as some kind of Fredholm determinant. And Peter Lax went around giving colloquia entitled "How Not to Prove the Riemann Hypothesis." He hoped, as I said, he hoped to realize zeta function as a Fredholm determinant, something he didn't succeed at. Because of his background in algebra, he stated everything in terms of quadratic forms, not operators. We'll get back to who did operators later. He emphasized the geometry in L2 so that the name Hilbert space given to the abstraction, not by Hilbert, but much later by von Neumann, is appropriate. The high points of his work on this is the Hilbert-Schmidt theorem. Schmidt was his student, and no doubt the most important is the spectral theorem for bounded self-adjoint operators. Poincaré was not only a mathematician, also a theoretical physicist and philosopher of science. He got a first degree at the École Polytechnique, continued his studies at the École des Mines, which sounds like what it is. It was the School of Mines. And he worked as a mining engineer while completing his PhD at the Sorbonne in mathematics under the direction of Hermite. His first great work concerned the theory of functions on the disk automorphic under discrete groups of Mobius transformations, which he called Fuchsian groups. He discovered the Poincaré metric and realized it gave one hyperbolic geometry, and so a concrete model of non-Euclidean geometry. In this regard, we have his famous description of how he realized this. At that moment, I left Caen, where I'd been living, to take part in a geological expedition organized by École des Mines. The circumstance of the journey made me forget my mathematical work. Arriving at Coutances, we boarded an omnibus for I don't remember what journey. Moment I put my foot on the step, the idea came to me without anything in my previous thoughts having prepared me, that the transformations I'd made use of to define Fuchsian functions were identical to those of non-Euclidean geometry. I didn't verify this. I didn't have time, since scarcely had I sat down on the bus that I resumed the conversation had already begun, but I was entirely certain at once. On returning home, I verified the result at leisure to salve my conscience. Beginning in 1882, he published a series of papers on this subject of automorphic functions, based on constructing functions automorphic up to a factor and taking a ratio of two such functions. Felix Klein, who was slightly older and more established, had studied automorphic functions by passing to the Riemann surface obtained by taking the quotient of the disk by the Fuchsian group. At first, they had a friendly correspondence, but it turned into a competition, and Klein drove himself to keep up. Of course, there was this young whippersnapper, but Poincaré was not your typical young whippersnapper. He drove himself so much he had a nervous breakdown, followed by severe depression, and he didn't really produce first-class mathematics after he failed in this competition with Poincaré. He objected to the credit Poincaré gave Fuchs And in reaction, Poincaré, who was quite generous, called general discrete groups of fractional linear transformation Kleinian groups. Poincaré's accomplishments are vast, but rather than make a bulleted list, I'll pick a subset of areas where he had seminal work. Before leaving complex analysis, I mentioned the uniformization theorem of Koba and Poincaré that says the only simply connected Riemann surfaces are the plane, the Riemann sphere, and the disk, one of the truly great theorems of mathematics. He was also a pioneer in the theory of several complex variables. In particular, he proved that in more than one dimension, the ball and Pauli disk are not conformally equivalent, even though both of them are simply connected. So the Riemann mapping theorem doesn't extend to more than one variable. He was a pioneer in the study of dynamical systems and its close relative, the theory of differential and difference equations. He has several results on asymptotics of solutions, and he was the first person to understand that hyperbolic systems can have what is now called chaotic behavior. So one should view him as the grandfather of chaotic dynamics. So there's this now probably 30-year-old book called Chaos, on work of Feigenbaum, Ruel, Smale, but the grandfather of that subject is clearly Poincaré. He has several books about celestial mechanics, and his work on the three-body problem is what first gained him wide fame because he got a prize from the King of Sweden for it. He wrote cogently on issues underlying statistical mechanics, and in this context proved the celebrated Poincaré recurrence theorem that if a phase space has finite volume, the system returns arbitrarily close to its initial condition after long times. He was the founder of modern algebraic topology. Following up on work of Schwarz and Klein, he formalized the theory of covering spaces and defined the fundamental group. He invented homology theory and proved Poincaré duality, and he stated the Poincaré conjecture. Actually, he didn't make it as a conjecture, he stated it as a theorem with a wrong proof, but it was quickly realized his proof was wrong and it became the Poincaré conjecture. Independent of Einstein, he developed much of the formalism of special relativity, and in particular, he was first to write down Lorentz transformations as explicit linear transformations, after which the Poincaré group is named. He proved Lorentz invariance of Maxwell's equations and claimed that Lorentz invariance of gravity, whatever form it would take, would require the existence of gravity waves, with none of the crucial details that come from Einstein's work. But he was actually the first person to specifically suggest that there would be waves of the gravitational field. In 1910, there was a big push for him to get the Nobel Prize in Physics. There were 58 nominations that year, and 34 mentioned Poincaré, including 6 former winners, which is particularly impressive because the prize was first given in 1900. So there was only 10 years of prizes. Now, of course, there weren't 10 winners because the Nobel Prize is often given to more than one winner, but it's still impressive. Behind the scenes, a non-winner, namely Mittag Leffler, who was quite powerful in Swedish science, used his influence, but in the end, the prize went to van der Waals. It's conjectured that 2 factors for it going to van der Waals was a preference for experiment over theory, and the fact that Poincaré didn't have a single notable achievement, but lots of very important achievements. And the Nobel Prize does tend to be given for usually one major result. That said, he was continued for further consideration and might have gotten the prize later if he hadn't died just 2 years later at age only 58. We end our discussion by mentioning the fact that despite one thinks of his work as chaos and algebraic topology as sort of being very newfangled, he was actually often opposed to new ideas in analysis. He was an opponent of Cantor's work, unlike Hilbert, who was a big supporter. Indeed, he's reputed to say, point-set topology, by which he meant Cantor's work, is a disease from which the human race will soon recover. This does describe his attitude, and the quote is so widely accepted. At one point, you could purchase a coffee cup with the quote on it. The historian of science, Jeremy Gray, who I respect, questions whether he ever said it. He also said the following, which if you think about Brownian motion and other modern things is particularly, we have seen a rabble of functions arise whose only job, it seems, is to look as little as possible like decent and useful functions. No more continuity, or perhaps continuity, but no derivatives. Yesterday, if a new function was invented, it was to serve some practical end. Today, they're specially invented only to show up the arguments of our fathers, and they will never have any other use. Okay, so that's the second group of three. In the 18th century, the centers of mathematics were France and wherever Euler happened to be. And in the 19th, France and Germany. In the 20th, we need to add the US, England, perhaps Russia. All these are large countries. But with trios of mathematicians, I can't pick a large country. It's natural to look at a small country. If you ask yourself, what's among small countries, which is the one that's most impressive mathematically, I'm not sure what you pick for the second most important. But it's absolutely clear the most important small country, mathematically speaking, is Hungary. Picking only three mathematicians from there isn't easy, but the deepest ones, at least to me as an analyst, at least from the first half of the last century, are clearly Riesz, Szego, and von Neumann. Of course, the Rieszes were brothers. So this trio has four people in it. That's why my groups of three add up to 22. Remarkably, F. Riesz was a student with Feyer, who's not on this list, but the other three, namely M. Riesz, Szego, and von Neumann, were all students of Feyer, and we saw last time he also had Erdős and Polya. So Friedrich Riesz was a Jewish-Hungarian mathematician. Indeed, all these Hungarians were also Jews. He was a Jewish-Hungarian mathematician whose students include Horváth, Rado, Renyi, and Nagy. He did his studies in ETH in Zurich and in Budapest, and then went to Göttingen, where he was very much influenced by Hilbert. In 1911, he was appointed to the University of Kosovar, but in 1920, in accord with a treaty that ended the First World War, the town that Kosovar in was ceded from Hungary to Romania. The town of Kosovar was renamed Cluj, and it was no longer Hungarian University, so a new university was established in Hungary at Szeged, and the faculty from Kosovar was invited to join. Riesz and Haar founded the Bolyai Institute in Szeged. He very much wanted a position in Budapest, which was Hungary's greatest university, but there was a policy in the university that you could have at most one Jewish professor in each department. And Feyer, who was his contemporary and had done this spectacular thing at age 19, was already a professor at Budapest and was indeed a professor till the end of the Second World War. In 1945, with the Russian occupation, anti-Semitism somewhat diminished and Riess was able to move to Budapest. He survived the Second World War despite roundups of those of Jewish heritage. At first, he was protected by his high status, and he moved to Budapest during the height of the roundup in Szeged, and he returned to Szeged when the roundup started in Budapest, and shortly after that, the Russians occupied Szeged, and while the Russians were no angels, they did not ship people, Jews, off to camps. Riess and his brother, as well as Haar, Koenig, and Feher, never married. And he told his student Kalmar he shouldn't marry, but should devote his life to science. As one of Riess's students reported, however, Kalmar did get married. This made Riess lose his temper. For a while, he was nervous and impatient to Kalmar. He calmed down. Kalmar's wife was also an able mathematician, and Riess liked her, as all of us did. He could see Kalmar's scientific goals had not been hurt by marriage. His 1955 textbook, Lessons on Functional Analysis, with Nagy was long a mainstay. They wrote it in French. They, of course, didn't write it in Hungarian because they wanted people to read it. They wrote it in French because Riess's other primary foreign languages were German, which was not acceptable after the war, and English, which was not acceptable under Soviet occupation, but it was soon translated into English and was a basic functional analysis text for many years, including when I was a student. He'd been polishing it for many years, as this story from Ray Lorch, who was an American mathematician who spent his career at Columbia, but was a postdoctoral visitor in Szeged in the 30s. Riess was a dangerous man with whom to collaborate in writing a paper or a book. He was constantly having new ideas on how to proceed, and the latest brainchild was his favorite. This would lead to disconcerting results for a collaborator who was perpetually out of step. An example was told me by Tibor Rado, his ex-assistant. During the academic year, Riess would lecture on measure theory and functional analysis. Rado would take copious notes. When the summer arrived, Riess would depart for a cooler spot. Rado would sweat it out for 3 months, writing up at Riess's request all the material to be published in the fall. At the end of September, Riess would put in his first day at the Institute, and Rado would come to the library to greet his superior, proudly carrying a stack of 800 pages, which he placed in Riess's lap with great satisfaction. Riess glanced at the bundle, recognized what it was, and raised his eyes with a mixture of kindness and thankfulness, and at the same time a spark of merriment, as if he pulled a fast one. "Oh, very good, very good. Yes, it's very nice, really nice. But let me tell you, during the summer, I had an idea. We will do it another way. You will see as I give the course. You will like it." This took place many years in a row. The book was not written until Riess, probably under the pressure of advancing age, wrote the book in collaboration with Nagy some 18 years later. He was a giant of functional analysis with contributions from 1907 for 30 years. Among his contributions are: he gave the first formal definition of a metric space, the first definition of a connected set, and understood that compact sets could be defined in terms of the finite intersection property. I want to emphasize, at the start of Riess's career, metric spaces had not even been defined. Nevertheless, as you'll see as we go along, he developed the notion incredibly far. He's responsible for what's sometimes called the Riess representation, namely that the Hilbert space is a dual of itself. something that was also discovered by Frechet. He proved what's now called the Rees-Markov theorem. Namely, he was the first person to find the dual of the continuous functions on 0, 1. He proved he's the Riesz of the Riesz-Fisher theorem, which is on L2 convergence of Fourier series, and the fact that one of the points of Lebesgue measure is that it allows completeness. He was the first person to write down Holder's inequality for integrals. He defined LP spaces. He named them LP after Lebesgue and found their dual. In fact, other than the dual of H1, virtually all the dual spaces of classical Banach spaces were discovered by Riesz. He discovered the weak star compactness of the unit ball in LP. He was the first person to define Hardy spaces, which he named after Hardy, and he discovered what's called Riesz factorization. He independently of Herglotz at the same time discovered the Herglotz representation theorem. He understood the factorization of positive Lorentz series that's called the Fayet-Riesz theorem. He and his brother proved the F and M Riesz theorem. He's the person who understood that operator theory was much better done as operators, not quadratic forms, because you could form products more easily. And he was the one who first formulated the spectral theorem as a theorem about operators, not quadratic forms. He found the resolution of identity form of the spectral theorem. He gave the first definition of compact operators and then proved something. Well, it's called the Riesz-Schauder theorem, but actually it's basically Riesz-Schauder made a small additional remark 20 years later that's essentially a complete understanding of the spectral properties of compact operators. He invented something called Riesz products. He's the one who realized you could define orthogonal projection by a minimization. He's the first person who defined and developed the basic theory of subharmonic functions, including what's called the Riesz decomposition of subharmonic functions. He's the first person to realize that if you have an operator on a Banach space and the spectrum has two components, then you can define projections associated with those two components that, while they don't have all the properties of spectral projections, go a long way towards them. He invented the theory of vector lattices, Riesz spaces, and their duality. He found a wonderful proof of the spectral theorem. He understood, he was a pioneer in using and exploiting Hardy-Littlewood maximal functions, including something called the Riesz-Sunshine lemma. And he proved improved version of their maximal inequality called the Riesz maximal inequality. And he was the one that realized that you could use the Hardy-Littlewood maximal inequality to get Lebesgue's differentiation theorem. He found a wonderful convolution rearrangement inequality. So that's F. Riesz. It's just staggering if you think about what he did. His brother Marcel Riesz, not surprisingly, was also a Jewish-Hungarian mathematician. His students were Cramér, Hiller, Frostman, Turing, Gording, and Hormander, who you may have noticed are all Swedish, actually. He was Frederick's younger brother and did his studies in Budapest under Fayet. The year after getting his PhD, when he was having trouble finding a job in Hungary, he was invited to visit Sweden by Mittag Leffler, spent the rest of his career in Sweden, at first in Stockholm, and then starting in 1926, he moved to Lund and was there till his retirement. His most famous result is the LP boundedness of the Hilbert transform, of which Hardy wrote him in 1923. Some months ago, you wrote, "I've proved two conjugate LP functions, da, da, da. I want the proof, Both I and my pupil Titchmarsh have tried in vain to prove it. Riesz proved this theorem in 1928, in fact, to show LP convergence of Fourier series. He proved the result originally for even integers using a very simple argument, and then used a special case of what's now called the Riesz-Torin interpolation theorem. He had a more general conjecture in his paper that was later proven by his student Torin. Interestingly enough, and then he used duality. Interestingly enough, before Riesz did this work, Kolmogorov had proven the Hilbert transform of an L1 function is weak L1, and at least with current interpolation theorem, this implies Riesz's result, but it wasn't realized till many years later. Besides this result, Riesz did the following. He wrote a definitive book on Dirichlet series with Hardy, although it should be confessed to say he wrote it is a slight misstatement. This is a wonderful book. It was for many years the standard reference on Dirichlet series, and it has a charming preface by Hardy saying that in 1913, he and Riesz sat down and sketched out the contents of a book they planned on Dirichlet series. Unfortunately, they were separated after that by the war. So Hardy finished the writing and published the book, putting Riesz's name on it, saying that he hoped Riesz wouldn't mind this. It was, of course, a wonderful book, and it was something they had plotted to do together. But he defined Riesz means. He actually proved before the work of Hahn and Banach, there's a Hahn-Banach type theorem for positive functionals that you may have seen, which actually is due to Riesz and predated their work. He used it to prove solvability of the Hamburger moment problem. He's responsible for the idea, at least, of Riesz-Torin interpolation. There's a criteria he invented for the compactness of subsets of LP. He's the other half of the F and M Riesz theorem. Like his brother, he was a lifelong bachelor. But the following story was told by an attendee at an orthogonal polynomial conference in Budapest. One evening, a group went out to a cafe and were chatting about math. A young woman approached them and said, "Excuse me, we're from Sweden," and decided you must be mathematicians. Our grandfather was from Hungary and was a mathematician. We wonder if you've heard of him. His name was Marcel Riesz. So this was a lifelong bachelor. The next of the Hungarian quadruplets is Zago. He was also a Hungarian Jewish mathematician. In 1913, when he was an undergraduate at the University of Budapest, his friend Polya, then a postdoc in Berlin, returned to Budapest for the holidays and told Zago his conjecture about the asymptotics of Toeplitz determinants. Shortly thereafter, in 1914, when Zago was 19, he proved what's often called Zago's theorem, a subject he and others include me, have often returned to. I have a book on Zago's theorem. When the paper was published the next year, Zago was actually serving as a lieutenant in the Austrian army at the front in the war. And quite remarkably, he found the second term in the asymptotics, sometimes called the Strong-Zago theorem, in 1953, 39 years after he found the first term. After agreeing in Budapest and a postdoc in Berlin, he was appointed a professor at Königsberg. But after the rise of the Nazis, he fled to the US, first to Washington University in St. Louis, and then 2 years later, he was made chair of the Stanford math department. The math department, when he came there, was a provincial institution. He turned it into a world-class one. He was the chair for over 20 years. He was the founder of the theory of orthogonal polynomials on the unit circle and a great expert on classical orthogonal polynomials. He was one of the great classical analysts of the 20th century. This is a wonderful picture. It shows Zago on the left and Polya on the right. And in these things are presumably, at least according to the story, contracts that they had just signed with Springer. There are famous books, problem books and analysis that were standards for 40 years, maybe longer, are still quite readable and interesting. And they had just signed the contracts. About 10 years ago, I gave a talk at NYU about Lovener's theorem on monotone matrix functions and expressed some sadness that Lovener had never been elected a member of the US Academy of Sciences. Peter Lax was in the audience and he said to me, you know, neither was Zago. I was incredulous, but I checked the Academy website and I confirmed it. So I asked Lax about it the next day. And he said to me, you know, in those days, the Academy was an old boys club. I'm not sure there was anyone in math from Stanford until Paul Cohn was elected after he got the Fields Medal. And Paul tried to fix that. One day I got a call. Peter, this is Saunders. That's McLean. Who is this Polya? Polya was elected, but by then Zago had Parkinson's and that was considered disqualifying. And you know, I think Zago is the deeper mathematician, in which I agree. Okay, this is a good place to stop. We will now take a 15-minute break, even though we've only done 9 of the 22, but we'll have less to say about many of the remaining. And we start again in 15 minutes. Thank you.
So thank you.